Greetings and welcome to the Chemistry 223 Exam 1 review, and this will be an exam review for the upcoming first midterm. The first midterm will cover chapters 13 and 14. I split 14 into two sections, which were chapter 14 part 1 and chapter 14 part 2. And in this exam, you'll be studying things and taking exam questions on things like equilibria, acids and bases separately, how to find the pH, for example, and also titrations and buffers. So it's an exciting set of material. Let's talk about the exam a little bit. If you are taking Chemistry 223 as an online course, then the online exam will have 20 multiple choice questions. You'll have roughly 3 to 4 short answer questions. That number might vary depending on what I decide to include, but something like that. And you'll get the access to the exam roughly a week before the deadline. And the Friday deadline at 9 a.m. is a hard deadline. You must turn it in by email by that time. I will return the midterm to you with a summary sheet at the end, which says how you're doing. I encourage you to look at the summary sheet to make sure, first of all, that all the grades that I entered in for you are correct, because I do make mistakes sometimes. True instructor confessions 101. But also, if you're missing a lab, it'll say that. Make sure you get your labs in for the lab completion bonus, stuff like that. If this is not an online class, I will talk more about the format of the midterm during class. And regardless of if this is an online class or a regular class, if you have questions on absolutely anything, I want you to reach out to me. Email is the best way. Ask the questions. Make sure that you know what's happening for the first midterm exam. Okay, without further ado then, let's start the review. What I'll do is I'll present these questions. There'll be some possible answers, and then I'll ask you to pause the video. And I encourage you to try the problems on your own first. And when you think you've gotten to a good point, you can unpause the video and we'll talk about the answers. All right, let's do this. First question, we place 0.010 moles of dinitrogen tetroxide in a 2-liter flask at 200 degrees Celsius. And after reaching equilibrium, the dinitrogen tetroxide concentration is 0.0038 moles per liter. Calculate Kc for the following reaction. And you can see that there's 5 possible answers down there. I encourage you at this point to pause the video and work on the question. And when you're ready, you can unpause the video and we'll talk about the answer. Pause the video now. At this point, I'm assuming that you've worked on the question and you want to think about the answer, so let's get into how you would solve this. This is the classic equilibrium kind of question, where you should set up the ICE table, and the equilibrium part of the ICE table will be the parts that you'll throw into the Kc expression. Now, the equilibrium constant expression, the Kc expression, for this reaction will be nitrogen dioxide squared in the numerator, and dinitrogen tetroxide by itself in the denominator. But you do need the equilibrium values to answer this question. Another kind of hidden thing here is that when you're dealing with ICE tables, you almost always want to use moles per liter. And you can see here that you have this many moles, 0.010 moles, in 2-liter flask. So the molarity will be initially 0.010 divided by 2. That will be the initial part of the N2O4. Make sure that you always use molarity in ICE tables. So anyway, here's my ICE table that I set up. Initial change and equilibrium is what ICE stands for. And again, I did take the moles of N2O4 and I divided it by 2 to get this number right here, 0.0050. Technically, it should have another sig fig. Anyway, that's one of the part that sometimes is kind of confusing at first. We don't have any nitrogen dioxide. The change part will go down by X for N2O4, and it will increase by 2X for NO2. And because N2O4 is what we start with, it will decrease, hence the negative sign, and nitrogen dioxide has to increase. Remember, at equilibrium, you can't have 0 concentrations of anything. Also, because of the 2 on the 2 NO2s, that's why it's going up by 2X. So at equilibrium then, we'll have initially what is 0.0050 minus X, and NO2 would be 2X. But in this problem, it states that the N2O4 concentration at equilibrium, 0.0038 moles per liter. So the first thing you need to do in this one is solve for what X is. So you start with 0.0050 minus X equals 0.0038. And to solve for X, you would then take 0.0050 minus 0.0038. That would equal X, and X comes out to be 0.0012. And you need X to solve for NO2 because 2X is how much NO2 is going to be there at equilibrium. So 2 times 0.0012 is 0.0024. So Kc, 0.0024 squared, divided by the equilibrium amount of N2O4, which was 0.0038. That's how you get 1.5 times 10 to the minus 3. This is a reactant favored equilibrium. K is much less than 1. The value E there, the negative number, is just in there for silliness. You can't have negative Ks. Ks will not be 0 or negative. They can be less than 1, absolutely, but not less than 0 or equal to 0 for that matter. So if you can do this kind of problem, you've got this stuff down. It's a little weird, I know, to see the 0.010 divided by 2, but it highlights the fact that you must use molarity almost all the time anyway in the ICE tables. In this question, we're given two equilibria. The first is nickel 2 carbonate, and it's breaking down to nickel 2 plus and carbonate ions, and you can see the K value. The second reaction is hydrogen carbonate reacting with water to make carbonate and hydronium, and that expression is a Ka expression really, but I've just listed it here as K2, which is fine. K2 4.8 times 10 to the minus 11th. I'd like you to take those two equilibria and find the equilibrium constant for this reaction right here, which is nickel 2 carbonate plus hydronium, making nickel 2 plus hydrogen carbonate plus water. And one of those 5 answers there will be the right one. So at this point, I encourage you to pause the video, pause it and work on the problem. And when you think you've got a good answer, unpause it and we'll talk about what the answer actually is. Pause your video now. Okay, I'm going to assume you've had a chance to work on the video and you want to talk about the answer, so let me be the one to help you out with that. Woohoo! Anyway, if you need to combine equilibrium, all right, what I usually do is I try and look at the given equations and see how well they match up with the desired equation, kind of like what we used to do with Hess's law and stuff like that in Chem 221. Here's what I mean by that. In this first equation, nickel 2 carbonate is a reactant, and we want nickel 2 carbonate as a reactant. So I'm going to assume that we're not going to do anything to the first reaction, all right? Nickel 2 carbonate solid only appears on a reactant in the first one, and we want it as a reactant in the desired equation, so I think we're going to be okay. But if you look at the second reaction, hydronium is a product, and in the desired reaction, we want hydronium as a reactant. So we're probably going to want to flip the second equation around. We're going to take carbonate and hydronium as reactants, and that will make hydrogen carbonate and water as products. So we're going to flip that reaction around. Now, when you flip an equilibrium expression, you take the inverse 1 over the old K value. So when we flip that around, we're going to go 1 over 4.8 times 10 to the minus 11th, whatever that is. That's going to give us the new equilibrium concentration. When we do combine those equations, we will multiply the K's together. We'll use 6.6 times 10 to the minus 9 as is, but we'll use basically 1 over 4.8 times 10 to the minus 11th for the second reaction. So here's what I did, all right? I used the first reaction as is, didn't touch it. Nickel carbonate goes to the ions, no problem. But I did flip the second reaction around, all right? Carbonate plus hydronium makes hydrogen carbonate and water. And if you combine these two together, all right, the carbonate on the reactant and the product side cancels. So the pieces that are left, nickel 2 carbonate plus hydronium, making nickel 2 plus hydrogen carbonate plus water, and that's exactly what we want in the desired reaction. So to figure out the net K, you take the first K as is, the 6.6 times 10 to the minus 9, but then you multiply by 1 over 4.8 times 10 to the minus 11th, or you can calculate that number, whatever it is. But you should get ideally to 2 sig figs a K net of 140. So this will be a product favored reaction. And what that tells you is that insoluble nickel 2 carbonate will dissolve in acid hydronium to make nickel 2 plus and hydrogen carbonate and water. Kind of a cool process. This question is one of the most difficult questions of the whole Chem 221 through Chem 223 series. I'm just going to let you know right off the bat. This question, though, does offer, while we talk about the solution, a lot of cool insights into equilibrium and what it means. So if you're a person that doesn't pause in my video, and I'm not bummed at all, but anyway, I really do recommend that you at least try this problem first, because the more you try it, the more then the answers will make sense. There's a lot of pieces from equilibria that come together in this question, and I just want to let you know it's a little bit crazy. In this reaction, we're looking at hydrogen plus iodine making 2HI, and the Kc, the equilibrium constant, 54.3, so product favored. Now, initially, we have a hydrogen concentration, an iodine concentration, and an HI concentration. Those are initial concentrations. And what we want to do in this problem is find the equilibrium concentrations of all 3 species. And you can see the different answer possibilities right there. Now, what makes this question a little weird is, first of all, equilibrium is weird, let's be honest. No, just joking. Profit back on. Equilibrium, powerful concept. No. Anyway, what makes this a little strange is that in most reactions, you know if the reactants are going to move to products or if products are going to go to reactants. But you don't know that in this reaction because you have all 3 species present. All right. So the first thing you've got to do is just determine Q versus K. You have to do a Q calculation to see which way the reaction is going to proceed. Because even if I look at that H2 and I2 and HI initial concentrations, I don't know if the H2 and I2 are going to be decreasing and the HI increasing, or will the H2 and I2 be increasing and the HI decreasing. Those are both valid possibilities, and that's what Q versus K is going to tell you. Now, once you have Q versus K, then you can set this up as an ICE table, all right? And it'll be initial, change, and equilibrium, all that kind of jazz. So again, I highly recommend that you at least attempt this problem. So pause the video, all right? And once you're ready for it, then you can unpause the video and we'll talk about how to solve this somewhat challenging problem. So pause your video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so man, let's get into it. As I said, this is kind of a crazy problem, but it's crazy because it's hard to know if the reactants will be decreasing and the products increasing, or will the products be decreasing and the reactants increasing. Because we have all 3 species present and none of them are 0. 0 would be easy, we know it'd go towards that one. It's really hard to say. So what we're going to do first is do a Q calculation using the initial concentrations. Q looks just like K. Q in this case would be HI squared divided by H2 and I2. All right. We'll get a number out of that and we'll compare that to K. If Q is less than K, then that means the reactants will be decreasing and products increasing. On the other hand, if Q is greater than K, then that means the product HI will be decreasing and the H2 and the I2 will be increasing. That will help us with the minus and plus x's of the change area when we do our ICE table. So once we know which direction it's going to go, then we can plug these things into the ICE table and figure it out. So let's see what this looks like. So the first step, like I said, is you need to calculate Q, all right? And at the top there is the initial problem with all the information we need. Now Q looks just like K, products over reactants. So Q would be HI squared on top, and we would divide by H2 and I2. So you can see that on this line right here, I put in the initial concentrations for all of the different reactants and products. And when you calculate this number, it's 69.7. Now, comparing 69.7 7 to K, 54.3, you can see that Q is greater than K. So that means we have more products than reactants for this equilibrium, all right? That means that the product concentration is going to have to decrease and the reactant concentrations will increase. So this means this reaction, this set of conditions, those concentrations are going to shift towards the left, towards the reactants. And we'll need that here in the ICE table. So the second step is we can now set up the ICE table. Now, ICE table, initial change in equilibrium, just as before, okay? Here are the initial amounts of H2, of I2, and HI. Now, why we needed the Q value is because you can see in change right now, it says plus X minus 2X. Normally, for most reactions, it would be minus X plus 2X because reactants are going to products, something like that. We needed the Q to tell that the products will be decreasing, i.e. negative 2X, and the reactants will be increasing, i.e. plus X. Without Q, that would be a difficult thing to assess. So you can see then at equilibrium, you have all of those weird values, concentrations right there. Once you have the equilibrium concentration values, that's when you set them equal to K. And K is a known value, 54.3. Products divided by reactants. The math is pretty funky here, but you can see here's the HI amount at equilibrium squared. And then in the bottom, you've got the H2 and the I2. And again, notice those plus X's and minus 2X's are super important. If you have that cool solve button on your calculator, I would totally recommend getting it out. However, I am a person that still believes doing it the old-fashioned way. It has some merit. So anyway, I put here the steps that I use to get this into a quadratic formula. And if you've done it right, and again, using my anal retentive significant figures, let's be honest, this is the quadratic formula that I ended up with. And at this point, then you can use quadratic formula minus b plus or minus square root b squared minus 4ac all over 2a, blah, blah, blah. Anyway, at the end, you'll get two answers out of the quadratic. In this problem, we had a positive x and a negative x. And remember in chemistry, x is negative means negative mass. Now in an ICE table, they're all moles per liter, but you can't have negative moles because that would imply negative mass. For that matter, you can't have negative volume. So no way in chemistry, no negative numbers. Quick review is that if you do a quadratic and you get two positive roots, then the smaller one is the one you want. But anyway, in this one, we don't have to worry about it. We just don't want the negative one. So x, 5.25 times 10 to the minus 4. And that's what we'll plug in up here to find the equilibrium values of our three reactants and products. So H2 would be 0.00623 plus that X, or 0.00676. I2 is that number. HI is that number. Woohoo! Answer is D. Oh my goodness. Now, kind of crazy. These problems are really great. If you can do this kind of stuff, you've got it down, all right? You did Q versus K to see what directions you're going to use. You plugged it in to find K using quadratic formulas or the solve button on your calculator, jazz like that. Pretty awesome. You can also, though, double check yourself at the end, because even as I look at this problem now, I'm like, whoa. So anyway, you can totally check yourself, because products divided by reactants at equilibrium should equal the equilibrium constant, 54.3. So you can see that's what I did right there. I took those equilibrium concentrations, plugged them in. Sure enough, Kc equals 54.3. Booyah! We got this problem down. So if you can do this, awesome. If you don't, though, don't worry about it. At least you can see the steps involved. Nothing you can't do. Here's a question. It's got a delta H, which is negative 18.8 kilojoules. It's got a Kc of 10.5, and there's the reaction, CH2Cl2 going to CH4 and CCl4. If the temperature on the equilibrium system is suddenly decreased, what's going to happen to K? Is it going to increase? Is it going to decrease? Or is it going to stay the same? Work on this problem on your own. I recommend pausing the video, and when you're ready to talk about the answer, you can unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've worked on the problem and you want to talk about the answer. Very, very cool. This question is a Le Chatelier's principle question. It doesn't say anything about Le Chatelier's principle, but that's what's happening. Temperature changes affect the values of K, okay? And what we're doing here is we have a reaction and we're suddenly cooling it down. The key for understanding this is to know what this part is all about. Now, delta H is enthalpy. The little zero means standard states. The enthalpy here has a negative number. That means this is exothermic. Heat is being generated in this reaction. And what I would do on problems like this is literally write in plus heat. Because if you do that, you can think about heat as a product, which I think makes more sense for Le Chatelier's principle. Now, if that delta H would have been a positive number, we would have written heat on the reactant side. But for this problem, we're going to write heat as a product. Now, in the question, you're suddenly decreasing the temperature. You're making it colder. And that's like moving or taking away heat from the system. And the system's going to get cold, all right? And if you go outside, you want to put a coat on if it's cold to keep you warm. Well, the reaction kind of tries to do the same thing here too. So if you cool this reaction down, that's like taking heat away. And the reaction's going to shift to make more heat. It's going to shift to the product side. And if it shifts to the product side, numerator is going to get bigger, denominator is going to get smaller, your K is going to go up. So again, I highly recommend that if you have this kind of Le Chatelier's question, you should actually write heat in. If delta H is negative, heat will be a product. If delta H is positive, heat will be a reactant. And then as you increase the temperature, that would be like adding heat. Or if you decrease the temperature, which is what we did here, it's like taking away heat. And remember, you take away something, the reaction's going to shift to the side that you're taking stuff away from. It's going to shift to the right, which means that K is going to increase, etc., etc. Here's a question. We're adding 0.535 grams of sodium hydroxide with a molar mass of 40.0 grams per mole to 100 milliliters of water at 25 degrees Celsius. What is the hydronium ion concentration in the solution? Just to make sure we're all clear, this little grams moles minus 1 means grams per mole. All right, that's just a notation that's sometimes used in science. This question is really about how to convert a hydroxide ion concentration to a hydronium concentration. So see if you can do this problem, all right? I recommend pausing the video. You can unpause it when you're ready to talk about the answer, and I'll go over it. Pause the video now. I'm going to assume you've had a chance to work on this. Let's get into the problem. We talked about in chapter 14, part 1, how all acids and bases are basically dictated and determined by Kw. Kw is the water autoionization constant. And at 25 degrees Celsius, which is where we're going to assume these problems are, hydronium times hydroxide equals Kw. And that value of Kw is 1.00 times 10 to the minus 14th. So if hydronium times hydroxide equals Kw, 10 to the minus 14th, we can use that 0.535 grams number to find the concentration of the hydroxide. So you can take 0.535 grams sodium hydroxide and divide by 40 grams per mole. That'll give you the moles of sodium hydroxide. Divide by 0.1 liters, which is 1,000 milliliters per liter if you turn 100 milliliters into liters. Moles divided by liters will give you the molarity of hydroxide, and then Kw divided by whatever number that is going to give you hydronium. You must know Kw, all right? It's just a number we're going to use over and over and over and over again. You must know what Kw is, okay? But anyway, if you do all those steps, the answer comes out to be 7.48 times 10 to the minus 14th. Here's the way that I calculated hydroxide, 0.535 grams divided by the 40 grams per mole. 1,000 milliliters per liter means that 100 milliliters would be 0.100 liters. So the concentration there, to way too many sig figs, but that's not what we're stopping at, is that number. Kw divided by that number, 7.48 times 10 to the minus 14th moles per liter. Very, very, very small amount of hydronium. As hydroxide goes up, hydronium goes down. And even though that doesn't look like a lot, 0.535 grams, in the chemical world, that's actually quite a bit, all right? And so that relatively high amount of hydroxide pushes hydronium way down, no problem. If you consider only the H2S and HCN equilibrium, and there's two Ka values right there, predict in which direction the following equilibrium lies. And this reaction is hydrocyanic acid reacting with hydrogen sulfide to make cyanide and H2S, which is hydrosulfuric acid. Anyway, the answers: equilibrium lies to the left, reactant side; equilibrium lies to the right, product side. It's perfectly balanced between left and right, or it cannot be determined. So try this problem, all right? See if you can play with those Kas. You got to know what a Ka means to answer this question. See if you can figure out what the answer is. I recommend pausing the video. When you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming that you've worked on this question a little bit. You want to talk about the answer, so let's get into it. This question really revolves around what a Ka is. And remember, Ka is an acid dissociation equilibrium constant. Kas are used extensively for weak acids. If K is less than 1, it means you have reactant-favored conditions, and both of these Ks are definitely less than 1. Now, there's a couple different ways to do that, but I'm going to show you what I think is the best way, all right? But it's not necessarily the only way. One way to do this would be to literally combine Ka expressions, all right? You would combine the Ka for H2S, and you'll end up using the Ka for HCN. But you have to be careful here. The reaction has HCN as a reactant, and H2S, the other acid, is a product. So what I would do here is I would write HCN, and if it's a Ka expression, HCN reacts with water. It makes the conjugate base, which would be cyanide, and hydronium. And that Ka expression there would be 4E minus 10. I can't write on this thing very well, so sorry, it's pretty cheesy, but hopefully you get the idea. I'm doing that because HCN is a reactant, and I want HCN as a reactant if it's a Ka, so this is really good. However, H2S, we want it as a product, all right? And H2S is not normally a product in a Ka. So I need to reverse the Ka expression for H2S. So what that means is I would have H2S and water as products now because I'm reversing it. And then the conjugate base, which is HS minus, and hydronium would be my reactants. And the K here would be 1 over the K for H2S, so 1 over 1E minus 7. All right, pretty funky. At this point, you could combine equilibrium. And so, for example, the hydroniums will cancel, the waters will cancel, and you can see that what's left, you've got HCN and HS minus, which is what we want as reactants, and cyanide and H2S would be the products, and that's what we want. And then to figure out K here, you'd get 4E minus 10 times 1 over 1 times 10 to the minus 7th. That would give you an equilibrium constant. I think you're going to see that it's reactant favored, which means shift to the left. That would be probably the ultimate way to do this problem. I won't lie. However, there is another way to do this problem, and it has to do with the strengths of acids. Acid strength always goes from strong to weak, all right? And if you look at this desired reaction, we have two acids, HCN and H2S, all right? The stronger acid is going to push towards the weaker acid. And strengths of acids, we can use literally the Kas. H2S has a lot bigger Ka. 10 to the minus 7 is small, but it's a lot bigger than 4 times 10 to the minus 10. So 10 to the minus 7 is going to push this reaction to the reactant side. And I didn't need to write out Ka expressions or anything like that. I literally just looked at the values of Ka. Bigger Ka is going to push to the smaller Ka. HCN has a smaller Ka. It's going to be on the left. So regardless of which way you do it, all right, this reaction is definitely going to be reactant favored. It's going to be pushed towards the left, all right? And you can actually figure out the equilibrium constant K by multiplying these two together. You'll get a number less than 1, which means reactant favored. Or you can literally just look at the strengths of Ka, and bigger Ka will push towards the smaller Ka. Down here I have a little advertisement. You could also do this with Kb's, and I didn't give you those in this problem, but you could also look at the Kb values. Bigger Kb is going to push to smaller Kb. Cyanide has a bigger Kb, 10 to the minus 5, than HS minus, which is 10 to the minus 7. So that's another way that you could also show this reactant is going to be reactant favored. Oh joy. In this question, we want to find the hydronium of a 0.10 molar hydrocyanic solution at 25 degrees Celsius, and the Ka for hydrocyanic acid, 4.0 times 10 to the minus 10th. All right, I recommend you work on this problem. Pause the video. You can work on the problem, and when you're ready to talk about the answer, you can unpause the video and we'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's do it. Weak acids, all right, don't contribute all of their moles to hydronium. We've seen that for Ka expressions, you take the acid and you add water to it on the reactant side, and the products will be hydronium and the conjugate base. So for this reaction, that would be HCN plus water, and it's in equilibrium with the conjugate base, which is cyanide, plus hydronium. And the question is, how do we get hydronium out of this equilibrium expression? And one way to do this was you could do the ICE table. All right, you're starting with 0.10 moles per liter of HCN and 0 cyanide and hydronium. Water is a liquid, so you don't need to worry about that. HCN will go down by X, cyanide and hydronium will go up by X, so you'll end up with X squared over 0.10 minus X equals Ka, 4.0 times 10 to the minus 10th. You can solve the quadratic formula, get an X value, and that X value will be hydronium. Totally fine. However, you can also make it a lot easier on yourself because 0.10 minus X is basically going to be equal to 0.10. We talked about in lecture how if 100 times K is less than C, you can totally do that. And 100 times Ka, 4.0 times 10 to the minus 10th, is 4.0 times 10 to the minus 8th. And that's a heck of a lot smaller than 0.10. So knowing that then, you can ignore that minus X by the 0.1, and hydronium will equal square root Ka times Ca. Another way you could do this is you could use one of my beloved short, quick, and dirty expressions for a weak acid. pH equals minus log square root Ka times Ca. You could solve for pH and then go 10 raised to the power of minus pH to get hydronium, or again, you could just do square root Ka times Ca. Totally up to you. But if you did all these problems, you should get answer B. Now you can see what I did is I used my beloved short, quick, and dirty expression, pH minus log square root Ka times Ca, and we will use that a lot. The pH comes out to be 5.20. You can check yourself. It is acidic. That's good. HCN is an acid, although not a very strong one. And then 10 raised to the power of minus 5.20 gives you 6.3 times 10 to the minus 6. Again, you could just use square root Ka times Ca to find the value. That would be fine too. And you could even use the quadratic formula. 4.0 times 10 to the minus 10th equals X squared divided by 0.10 minus X. Use that solve button. Your call. But hopefully at the end of the day, we'll all end up with the same answer. Life is good. In a 0.15 molar solution of sodium carbonate, what are the hydronium, the hydroxide, and pH values? And there's a Kb for carbonate. It's 2.1 times 10 to the minus 4. All right, I would recommend working on this problem, see how far you get. You can pause the video, and after you've worked on it, you can unpause the video and we'll talk about the answers. Pause the video now. Okay, I'm assuming you had a chance to work on the problem and you want to talk about the answers, so let's get into it. First of all, what the heck kind of chemical system do we have here? That might be a question you're asking. And it's a pretty easy question to answer because you have a KB. KB stands for base. So carbonate, the sodium carbonate, that's a base, all right? It's going to affect the pH. pH should become more basic, all right? The KB value there, 2.1 times 10 to the minus 4, isn't the smallest one. However, 100 times KB would be 2.1 times 10 to the minus 2, and that number is less than 0.15 the CB. So like we did in the last problem, if you'd like, all right, the hydroxide ion concentration is going to equal square root KB times CB. And that's how you could find the hydroxide value there. You could also use the quadratic formula if you'd like, but that would, whatever, that's cool. Anyway, once you have hydroxide, all right, there's a couple things you could do. You could find hydronium. Hydronium equals Kw divided by hydroxide. And once you have hydronium, minus log of hydronium will give you the pH. And if you did all those steps, that's fantastic. And that's a really cool way to do it. But let's think a little bit more about what it means to be a base, and this is a basic solution. If you look on the far right column, there's 4 possible answers, but they repeat, like there's 2 5.61s and 2 11.75s. If this is a base, the pH is going to have to be greater than 7. There's no way that answer A or answer D is going to fly, because a base has to have a pH larger than 7. So we're automatically going to disqualify A and D here. Those would be acidic pHs. That's not going to work. Now, you can even go farther than this. If it's a base, your hydroxide concentration should be a bigger number than your hydronium concentration. So if you look at B and C, B has a smaller hydronium than the hydroxide. 10 to the minus 12 is certainly smaller than 10 to the minus 3. C has a larger hydronium than it has hydroxide. C, if it has more hydronium, that means you're going to have an acid. You're not going to have a base if you have more hydronium than you have hydroxide. So by default, you can say answer B. Here's the actual work you can do to do this, and that's probably the better way. All right, and you can see what I did in this problem is I used one of my beloved quick and dirty expressions, the pH of a weak base, which is 14 plus log square root Kb times Cb. You are justified in using that because 100 times K is less than C. That's where the 11.75 came from. Then hydronium equals 10 raised to the power of minus 11.75. That's where the 1.8 times 10 minus 12 number came from. And hydroxide equals Kw divided by hydronium. That would be 5.6 times 10 to the minus 3. Again, you could have found hydroxide first. Hydroxide would be square root Kb times Cb and worked your way to hydronium and pH. There's many different ways to do it. But again, sometimes if you just think about these problems, we automatically kicked out the other 3 answers. They didn't make sense. If it's a base, you must have a basic pH. And if it's a base, your hydroxide needs to be a bigger value than your hydronium. Right? That's what a base is. So there's a couple different ways to solve it. Any of these ways are awesome. Cool. Here are 4 acids with 4 pKa's, and I'd like you to put them in order of increasing acid strength. Now remember, pKa is related to Ka, and Ka is related to the strength of the acid. So think about those 4 values right there and put them in order of increasing strength, weakest to strongest. All right? Pause the video, work on this question, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've had a chance to work on the problem. You want to talk about the answer, so let's get into it. These are pKa's. They are not Ka's. If they were Kas, then the biggest Ka would be the most acidic, all right, has the most hydronium, and the smallest Ka would be the least acidic. But this is a px scale, and for pH, which is hopefully the most familiar to you, smaller numbers mean more acid, and bigger numbers mean less acid. So because these are pKas, the strongest acid here will have the smallest pKa. 2.98 should be the smallest one. The biggest pKa will be the weakest acid. So of these problems right here, you want to go from biggest pKa to smallest pKa. And I believe that's going to be D, A, B, C. I believe the answer here is D. Now, if you can see pKa versus acid strength, that's the best way to do this, all right? And just like pH goes down, acid goes up. Well, pKa goes down, acid goes up as well, because Ka is related to the strength of the acid. But if you don't know, there's nothing wrong with converting these pKas into Kas. So you could go 10 to the minus 4.60 to get the Ka for the aniline ion there and answer A. You could go 10 to the minus 3.09 power to get the Ka for that one, etc., etc. And from there, you could go smallest Ka to biggest Ka for smallest acid to strongest acid. So either way you do this is cool. It does help. There's a trend in organic chemistry, I feel, that talks about acids more in terms of pKa than anything else. So knowing this trend can be helpful in later classes. Here's a list of possible ions and molecules. I'd like you to classify the following as Lewis acids or Lewis bases, all right? And there's 4 reasonable answers and also my silly public enemy number 1 answer, which is unfortunately not right. Anyway, think about this problem. I recommend you pause the video, work on the question. When you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've had a chance to work on the question. You want to talk about the answer, so let's do it. Lewis acids can accept lone pairs of electrons. They're lone pair acceptors. Lewis bases are lone pair donators. They have a lone pair that they can donate. So one way you could do this problem is just go through up there and see which ones have lone pairs on them or which ones could be Lewis acids. And ammonia, if you draw out the Lewis structure, that nitrogen has a lone pair on it. Ammonia is a wonderful Lewis base. Chloride has 4 lone pairs around it. It's basically just bristling with lone pairs, or it's got all the lone pairs it needs. Chloride would also be a Lewis base because it has a lot of lone pairs. Now, acids usually fall in one of 2 categories. One of the categories is transition metals. Transition metals, as well as lanthanides and actinides, are great Lewis acids. They'll have lots of empty orbitals for electrons to be shoved into. So anytime you see a transition metal, you can basically think of that as a Lewis acid. The other category, though, are the group 3A twisted metals. I've been calling them since Chem221. That's an unofficial name, of course, but twisted metals usually have an empty p orbital that you can shove electron density in. So things like boron and things like aluminum and gallium, those are going to be great Lewis acids as well. So in this category, I would go acid for BH3, base for NH3 and chloride, and then acid for aluminum and chromium. I think the answer is going to be A, all right? Acid, base, base, acid, acid, all right? Couldn't resist throwing a picture of Public Enemy just because that's who I am. Sorry about that. Every time I think of base, I think base. How looking? Okay, well, anyway. Hopefully you get the idea. Pretty chill to find them. Cool. We have a solution of ammonium chloride. What effect will happen if we add ammonia to the pH? So the pH will be affected probably by the ammonia. What will be the effect? It can increase the pH, it can have no effect on the pH, or it can decrease the pH. Or maybe we can't tell. See if you can answer this question. I recommend pausing the video. You can think about it a little bit. When you're ready to hear the answer, unpause the video. We'll talk about the answer. Pause your video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's get into it. Okay, on questions like this, you basically ignore what was already there because we just want the effect upon adding, in this case, ammonia. So you only need to think about what the effect of what you're adding will be. And in this case, NH3, as we've seen, is a base. It's a weak base, it's a Lewis base, all that kind of stuff. It's a base. And anytime you add a base, it's going to make your pH become more basic. It's going to increase the pH. We don't know how much it's going to increase the pH, maybe just 0.000001 units, or maybe, 2 units, who knows? But we know it's a base. Bases increase the pH, and that's the end of this problem. That's literally it. If we would have added an acid, it would have decreased the pH, and there are some compounds that don't affect pH too, but ammonia definitely going to increase the pH. We have a solution of ammonium chloride. What effect will the addition of NaCl have on the pH of the solution? And like before, maybe it's going to increase the pH, maybe have no effect, maybe decrease the pH, or maybe we can't tell. So try this problem. I recommend pausing the video. When you're done thinking about it, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you had a chance to work on this question and you want to talk about the answer, so let's get into it. Like the last problem, you can ignore the ammonium chloride, all right, because we don't care what's going on there. We just want to know what the effect will be upon adding NaCl to the solution, all right? Well, NaCl, you have to think about the ions, all right? So for example, if it was ammonium chloride, ammonium is the conjugate acid of ammonia. So if we were adding ammonium, that was adding an acid, it would decrease the pH, become more acidic. Chloride, on the other hand, chloride is the conjugate of hydrochloric acid, and conjugates of strong acids and strong bases don't affect pH. So chloride, in both ammonium chloride and sodium chloride, chloride has no effect on the pH. Chloride, you can think about it as being the conjugate base of hydrochloric acid. Sodium ions can be considered the conjugates of sodium hydroxide, a strong base. And all conjugates of strong acids and strong bases do not affect pH. So sodium chloride will have absolutely no effect on the pH of the solution. And we know that because sodium is the conjugate of sodium hydroxide, chloride is the conjugate of HCl. And both of those are very, very strong. They push the equilibrium back to the original ions. They have no effect on the pH. So that's kind of a cool way to see what's going on. Here are 5 possibilities for a buffer solution. Which one of those would be an ideal buffer solution? Think about what makes a good buffer to answer this question. Okay, I recommend pausing the video. You can think about this problem, work on it, and when you're ready, unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's get into it. In a buffer system, you must have 2 requirements. First of all, the buffers have to have only weak acids and weak bases, no strong acids or strong bases. Strong acids and strong bases push the equilibrium too hard, so they don't coexist well with each other. The other thing you have to have, though, is you have to have conjugates. You have to have an acid with its conjugate base or a base with its conjugate acid. So as I look through these questions, I see a lot of strong bases and strong acids. Sodium hydroxide is a strong base, HCl is a strong acid, KOH is a strong base, HCl is a strong acid. So right away, answers B, D, and E are kicked out, all right? None of those are going to work because they have a strong acid and or a strong base. So we're down to A and C. And remember that you have to have conjugates of each other. And conjugates are just 2 chemical systems related by plus or minus a hydrogen. Well, if you look at C, you've got essentially acetic acid, and this thing right here is formic acid, which you don't need to know. But if you look there, for example, there's extra hydrogens and carbons in the acid relative to HCO2H. Those 2 two are not conjugates of each other. First of all, they're both acids, which is a no-no in these kind of things. You have to have conjugates of each other, so C isn't going to play. Now, A at first maybe doesn't look like conjugates, but remember potassium of potassium cyanide. Potassium is a spectator ion, and in solution it will drop away. K plus is the conjugate of KOH, so it won't affect your pH. And as K plus goes away, you're going to have cyanide. So cyanide plus H plus makes hydrocyanic acid, HCN, and HCN minus H plus makes cyanide. So the answer here is definitely A. Those are the conjugates of each other. Don't have any strong acids and strong bases in your buffer. The two systems must be conjugates. They can't both be weak acids, which is what ended up happening there on C. Pretty crazy. But this is a good way to then pick out which one of those would be the best buffer system. So here's another buffer question. What would be the pH of a buffer that has 0.20 molar ammonium chloride and 0.20 molar ammonia? And it gives the Ka for ammonium there, 5.6 times 10 to the minus 10th. There are a couple different ways to solve this problem. I would recommend using the Henderson-Hasselbalch equation because I'm in love with that equation, let's be honest, if you've watched the lectures. But anyway, it's a very quick way to find the pH of a buffer system. So I recommend that you pause the video, work on this a little bit, and when you're ready to talk about the answer, you can unpause the video, pause the video now. I'm assuming you've worked on the problem, you want to talk about the answer, so let's do this problem. Okay, like I said earlier, there are a couple different ways you could do this problem. You could set this up as an ice table, all right? You'd have ammonium chloride plus water basically making ammonia and hydronium and chloride, and you pull the chloride out. You have both ammonium and ammonia. Ammonium will go down because you have to make some hydronium, so ammonia and hydronium would both increase by X. At equilibrium, you'd have 0.20 minus X for ammonium, and ammonia would be 0.20 plus X, and hydronium would be X. You'd set that all equal to 5.6 times 10 to the minus 10th. You could go through quadratic. You could pull out the plus X and minus X like we talked about in lecture, etc., etc. However, I highly recommend you start thinking about the good old Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, pH equals pKa plus log, and it's base over acid. And again, I can't draw very well in this thing, so bear with my bad handwriting. pH equals pKa plus log base over acid. Now, pKa comes from Ka, so minus log of 5.6 times 10 to the minus 10th, that's going to give you the pKa. Now, base over acid. Base and over acid can be moles per liter over moles per liter. It can also be moles over moles. In this problem, it makes sense to have moles per liter over moles per liter. So 0.20 divided by 0.20. Notice that it is log of 0.20 divided by 0.20 or log of 1. Log of 1 in your calculator is 0. So in this problem, pH is going to equal pKa. So when you figure this problem out, 9.25. If the base and acid concentration, i.e. the ammonia and the ammonium, are the same, then pH equals pKa. So minus log of 5.6 times 10 to the minus 10th is 9.25. That's how you're going to find pH here. This question is similar to the last question, but now you do have unequal quantities of ammonium and ammonia. So this question is similar to the last one. We want to find the pH of this buffer. However, now we have ammonium at 0.20 moles per liter and ammonia of 0.950 moles per liter. Remembering that pH equals pKa plus log base over acid, I would use the Henderson-Hasselbalch equation. The base is ammonia, the acid is ammonium, all right? And from there, you can find what the answer is going to be. So I recommend you pause the video, work on this question a little bit, and when you're ready to talk about the answer, unpause the video and we'll see what's going on. Pause the video now. Okay, I'm assuming you've worked on the problem, you want to talk about the answer, so let's do it. So again, what I would recommend for this question is the same as the last one. pH equals pKa plus log base over acid, okay? And the base here will be ammonia, and the acid will be ammonium. So you'd have log of 0.50 divided by 0.20. You can use the same pKa from last time, etc., etc. Anyway, if you do all this problem out, then you end up with a pH of 9.65. And at first it might seem kind of weird, some of these numbers, but the last problem, pH was 9.25 when the ammonium and the ammonia were equal concentrations. And notice in this problem, we have more ammonia, more base, okay? So our pH should be more basic than it was last time. It should be more basic than 9.25, and it is. So that's some ways that kind of make me feel better about problems like this. You have a more basic pH because you have more base than you had before. So that's kind of a cool thing. In this question, we want to find what volume of 0.10 molar sodium acetate must be added to 100 milliliters of 0.10 molar acetic acid to have a pH of 4.00. Okay, again, this is a problem where there's multiple ways to kind of solve this kind of thing. Again, I would probably recommend using Henderson-Hasselbalch, but again, that's just kind of my way. Anyway, I do recommend that you pause the video, work on the question a little bit. When you get an answer, you can unpause the video. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on the question and you want to talk about the answer, so let's get into it. I'm a big Henderson-Hasselbalch fan, as I've told you multiple times already. So for this problem, what I would do is I would start with the mole version of the Henderson-Hasselbalch, and that's pH equals pKa just as before, but in the previous problems we use moles per liter over moles per liter. In this problem, I'm going to use moles over moles, and that's something you can do with HH. So instead of base over acid in molarity, now we're going to have moles of base divided by moles of acid. And you're probably like, well, that doesn't seem any better, and I totally understand. Moles, all right, moles equal the concentration, molarity, times the volume, all right? So instead of writing moles of base, you can also write the concentration of the base times the volume of the base. And for moles of acid, you can write concentration of acid times the volume of acid. Okay, now if you look at this question, all right, I'm going to use different colors. You have the pH 4.00, and that's what goes right there. You can turn 1.8 times 10 to the minus 5 into pKa minus log of that number, and that's going to give you pKa. Volume times concentration of acetic acid, all right, that's this part right there. And if you want, you can even use 100 milliliters. That's totally fine, because the top part, if it's in milliliters too, you'll be okay. And the base, which is the acetate, that's concentration of the base. So if you look carefully, the only thing you don't have then is volume of base. So pH 4.00 equals pKa, whatever minus log 1.8 times 10 to the minus 5 is, plus log, and in numerator, 0.10 times x, which is going to be the volume of your base, and in the denominator, 0.10 times 100 milliliters. And you can literally go through them and solve for the volume of the missing base. So let's see what the math looks like. What I did here is I first solved for the pKa, and minus log of 1.8 times 10 to the minus 5 is 4.74. And that's the number that we're going to put in here in a little bit. Now, acetate is the base and acetic acid is the acid, all right? So base over acid means acetate divided by acetic acid. And you can see what I did. I went concentration times the volume, and we don't know the volume of the acetate, VACE, all right? But we do know the volume and concentration of the acid, all right? And I actually went through and solved that in this version of the problem, which is cool. So then Henderson-Hasselbalch, pH equals pKa plus log base over acid. Well, here's the pH 4, here's the pKa we calculated, plus log base over acid. Here's the concentration times the volume, and here's the moles of the acid in the bottom. So I'm basically trying to solve for the volume of the acid. So the first thing you do is you go 4.00 minus 4.74, and that comes out to be minus 0.74, and that equals log 0.10 times V divided by 0.010. Then you can do the anti-log, and base 10 log is 10 to the x. So that gets rid of the log on the right side. Then you go 10 to the power of minus 0.74 on the left. And this is just fun for your calculator, okay? 10 to the minus 0.74 is 0.182. And that equals 0.10 times V divided by 0.010. You want to solve for the volume of the acetate. So 0.182 times 0.01 divided by 0.10 comes out to be this number, 0.0182 liters. Because I used liters up with the acid, my answer came out with liters. If you use milliliters, you'll get the milliliters right away. Anyway, 2 sig figs, 18 milliliters. This is kind of a cool little handy thing sometimes with buffers. If you just want to know the volume to add to make the buffer, this is neat. You have to know that moles equals concentration times volume, but once you do that, plug and chug, you're good to go. Here's a graph, and it represents one of the types of titration that we looked at in the lab. And I'd like you to tell me which of those 5 combinations it could be. So again, if you need to, pause the video, think about this question, and when you're ready to think about the answer, unpause the video, we'll talk about it. Pause the video now. Okay, I'm assuming you worked on the problem, you want to talk about the answers, so let's get into it. Okay, so first of all, the pH is the y-axis, and you can see that it goes from 0 to 14 supposedly, while the volume of the titrant there goes from 0 to 40. Now, when I look at a graph like that, first of all, I want to see where the pH is starting. And this pH is starting at a pH greater than 7. That means basic, all right? And in the types of titrations we looked for, what you start with is always listed first. So it will not be a strong acid, strong base. Strong acid, strong base would start out acidic. It also won't be a weak acid, strong base, because even weak acids would start acidic, not basic, okay? So we already eliminated A and C. Let's think about now what else is going on. After I figure out what you start with, the next thing I look at is where is the equivalence point pH of the titration. And that's what that little dot right there is. It's the middle part of the steepest part of the titration, if you will. And that equivalence point pH will be a hint. And if you go over on your y-axis, all right, whatever pH it is, it's certainly less than 7. Now, a strong base plus strong acid titration would have an equivalence point at 7. And this one is certainly less than 7, so this isn't a strong base plus strong acid titration. Now for the remaining 2 types, all right, we did not look at weak base plus weak acid titrations. That's a whole nother ball game. You have to think about Kas. They're kind of unwieldy and they're not used very much, to be honest. So don't even think that's a possibility. The only one here that fits is the weak base plus strong acid. And again, what I did, you can see I even highlighted it there. I looked at that equivalence point pH. It's basic. I looked at that equivalence point pH and it's acidic, all right, it's less than 7, okay? So that means that, yep, all of the weak base has turned into its conjugate acid. So at equivalence, when the moles are equal to each other, you do have an acidic pH, no problem. In this question, we're mixing 15 milliliters of 0.4 molar HCl with 15 milliliters of 0.4 molar ammonia. What is the pH of the resulting solution? And there's a Kb value. Now, this is the kind of problem that I'd like you to be able to do after you're done studying all this material. You've got 2 random acids and bases, you're putting them together, and you should be able to calculate the pH of the resulting solution. Now, to make your life easier, I would think about this as a a titration problem. It's not a titration problem, but if you figure out what kind of species you have, like strong acid plus strong base or weak acid plus strong base, whatever, you can then go through and find the corresponding equation from that region. So first of all, find out what kind of quote-unquote titration it is. Second of all, see where you are in the titration so that you can use the right equation to find the pH. So I recommend you try this problem. Pause the video. When you're ready to talk about the answer, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on the problem and you want to think about the answer a little bit. So hey, let's do it. Let's talk about how to solve this problem. Again, if you see a question like this, all right, it's literally just a random acid and base being put together. And figuring out from cold scratch would be maybe kind of tough, but you can use those titration calculations to actually solve problems like this. And this is not a titration question, but all of the methodology that we developed in that lab will help you here. So if you look at this question, all right, HCl is a strong acid, and ammonia, because of the Kb, you know it's a weak base. So this question is a weak base plus strong acid titration-like question, all right? It's not really a titration, but we're going to assume it's a titration. Now, once you know it's weak base plus strong acid titration, then you have to figure out which region you're in, and the regions are just based on moles, all right? And if the moles of ammonia and HCl are equal, it's equivalence. If it's under, then it's pre-equivalence, etc., etc. Well, you can probably see that in this question, the volume and the concentration for the strong acid are equal to the volume and concentration of your weak base. That's kind of cool to know, because if the volumes and the concentrations are equal, then that means you're at equivalence. So at equivalence, the moles of HCl and ammonia are equal, and HCl has wiped out all of the ammonia. But in the process, the ammonia has been turned into ammonium. Ammonium is a weak acid. So in this problem, to solve for the pH, we're going to use the pH for a weak acid, and pH equals minus log square root Ka times Ca. That's the basic form of the equation we want here, okay, because it's a weak acid, ammonium. Now, there's obviously some issues. We don't have Ka, we have Kb. There's nothing here about a concentration of an acid. It's not the concentration of HCl, it's the concentration of ammonia. Well, we can turn a Kb into a Ka because Kw equals Ka times Kb. So Ka equals Kw divided by 1.8 times 10 to the minus 5. No problem. Ca, the concentration of ammonia, we need to know the moles of ammonia, and we need to know the total volume. Now, moles aren't too bad. You can use either HCl or ammonia. You can take the liters of HCl and multiply it by the moles per liter of HCl, for example, to get the moles. You could also do the same thing with ammonia. Ammonia moles have all turned into ammonium at this point, and that's why we can do it. Now, the volume isn't too hard in this problem because we have the two volume amounts. They're both 15 milliliters. You want to make sure you use liters, so we'll use 0.0300 liters. That's what you want to do to solve a problem like this. So here's the work, all right? First of all, you have to realize this is a weak base plus strong acid, quote-unquote titration. It's not really a titration, but that's what we're going to assume it is. And once you know that, the next thing to do, figure out the moles, figure out which region you're in so you can use the right equation, all right? This equation, as you can see, the moles of strong acid and weak base are equal, so it's equivalence, all right? We expect the pH at equivalence to be less than 7 because the ammonia has turned into ammonium, and ammonium is a weak acid, so the pH should be acidic. Now, pH, this is the equation from the lab. It's pH equals minus log square root Kw divided by Kb times NWV divided by total volume, etc. You can also, if it's easier, just use this one right here because that's really what this is, all right? You can see that Ka has been turned into Kw divided by Kb. We talked about how you found the moles moles from volume in liters, divide by the total liters. If all is said and done, again, remembering that your pH should be acidic, 4.98. Cool. So if you can see how this process works, and I'm hoping you can see the utility of those crazy titration calculations. Not everybody does titrations, okay? I do titrations because I'm a chemist, but most people don't. But if you do mix random acids and bases together, you can quickly find the pH using the titration calculations. And that's where there's some real value, I think, in figuring that stuff out. Here's a problem. 0.40 grams of sodium hydroxide, again with a molar mass of 40 grams per mole, mixed with 100 milliliters of 0.10 molar acetic acid. What is the pH of the resulting solution? And there's a Ka value. 5 possible values for the pH. I recommend that you try this problem on your own. Pause the video, work on it a little bit, and when you're ready to talk about it, you can unpause the video. We'll see what's up. Pause the video now. At this point, I'm assuming you've had a chance to work on the problem and you want to talk about the answer, so let's get into it. There's a couple different ways to do this problem, all right? And the way that I would probably approach it is I would think about this as, again, a type of titration. Acetic acid is a weak acid. It has a Ka right there. And sodium hydroxide is a strong base. So this would be like a weak acid plus strong base titration. And it's not a titration, all right, but we can use the equations from there to figure it out. Now, once we know this is weak acid plus strong base, we need to look at the moles, all right? And the mole relationship will then tell you which one of the regions you're in, okay? Now, for sodium hydroxide, that would be 0.40 divided by 40 grams per mole. That would tell you the moles. And then for the acetic acid, you'd take 0.1 liters times 0.10 moles per liter. That will tell you the moles. And from there, you can find the corresponding region, all right? If the moles are equal, it's equivalence. If you have more acetic acid than sodium hydroxide, it's pre-equivalence, etc., etc. That's what I did here in this problem. So first of all, I realized it's weak acid plus strong base. I then found the moles, and lo and behold, the moles are equal to each other. So if the moles of weak acid and strong base are equal to each other, this is the equivalence point. That means that the acetic acid and the sodium hydroxide have wiped each other out, and we now have acetate as the active pH species. Acetate is the conjugate base of acetic acid, base being the operative word. This is going to be like a pH of a weak base. Also, our answer should be a basic number, a number greater than 7. So you can pull out the acidic pHs there, by the way. Anyway, for weak bases, the general equation is pH equals 14 plus log square root Kb times Cb, and this is the equation from the lab, and they are the same thing. So like Kw divided by Ka, that's where Kb comes from. Like we saw in the last one, concentration of the base, you want to take the moles, and you can use weak acid or strong base because they're equal, divide it by the total volume. There's only one volume in this problem, which is the volume of the acetic acid. The grams of sodium hydroxide don't contribute to the volume overall. But anyway, throw all that in there. 8.87 is your pH. It's basic, which is good. It should be basic because at equivalence, the weak base of this acetic acid should dominate. Cool for school. In this question, we want to find the pH of a solution when 50 milliliters of 0.10 molar HCl and 100 milliliters of 0.10 molar sodium cyanide are mixed. And there's a Ka for hydrogen cyanide, 4.0 times 10 to the minus 10th. All right, using the ideas we've looked at so far, see if you can solve this problem. I recommend pausing the video. You can unpause it when you're ready to talk about the answer. Pause the video now. Okay, at this point, I'm assuming you've worked on the problem and you want to talk about the answer, so let's do it. Okay, so again, this is just some random acid and base coming together, but we can use the titration calculation equations to figure out what this pH is going to be. Now, HCl is a strong acid, and sodium cyanide, all right, well, it gives us the Ka for cyanic acid, HCN, and notice that HCN without H plus is cyanide. So cyanide here is a weak base. So this is a weak base plus strong acid titration, if you will. It's not really a titration, but those are the equations we're going to use. Now, in order to figure out which region you're in, you have to use the moles. And if you look at these numbers carefully, the concentrations of both the strong acid and the weak base are both 0.10, but the volumes are certainly different. We have less HCl than we have the base. So if we have less HCl and the concentrations are the same, that means we're going to have more moles of the base than we have moles of the acid. So this is the so-called pre-equivalence region of the weak base plus strong acid, where you have more moles of weak base than you have moles of strong acid. For questions like this in this pre-equivalence region, I prefer to use, personally anyway, a version of the Henderson-Hasselbalch. And Henderson-Hasselbalch, pH equals pKa plus log. Now, Henderson-Hasselbalch is moles of base over acid, okay? And we absolutely do have moles of base. I'm going to put moles weak base, but the strong acid lowers the moles of the weak base. The strong acid goes after that. In the Henderson-Hasselbalch, one of the variants was you can write NWB minus NSA, and on the bottom you'd write NWA plus NSA, moles of weak acid plus moles of strong acid. Now, we don't have any moles of strong acid, so the NWA, the moles of weak acid, is just equal to 0, but we certainly have some moles of strong acid. So that's a very sloppy NSA. You can look at a better version in the titration calculations handout. But anyway, you can see here a couple of things. pH is going to depend on pKa, so you need to turn this into minus log for that number to get pKa. Also, we're going to need the moles of everything. Moles of strong acid HCl and moles of weak base cyanide. If you do all of that, all right, here's the work that's involved. So first of all, recognize that it's strong acid and weak base coming together. Here's the moles of strong acid and the moles of weak base. Definitely more moles of weak base than strong acid, so it's pre-equivalence region, okay? You could go through and do what I did. pH equals pKa plus log, and it was moles of weak base minus moles of strong acid on top divided by moles of strong acid. However, if you look at mathematically, 0.010 minus 0.0050 divided by 0.0050, well, 0.010 minus 0.0050 is 0.0050, and 0.0050 divided by 0.0050 is 1, log of 1 is 0. So what that means, pH equals pKa. So in this problem, all you really have to do is go minus log 4.0 times 10 to the minus 10th. I didn't honestly think about that while I was talking about that here, but that makes a lot of sense. pH and pKa are the same. This is the so-called half equivalence region. I was having you do the full version, which honestly is more thorough and probably better just to be safe. But in this problem, as I just realized, you really just need the half equivalence, pH equals pKa. So anyway, lots of advantages for doing these different things. Again, there's nothing wrong with going pH equals pKa plus log, all of that stuff, but honestly in this problem it would have been better just to realize it was half equivalence. pH and pKa are the same. More than one way to get to government camp, and I took the little bit longer way. If you saw this with half equivalence and went straight pH equals pKa, good to go. Here's a question. We're adding 40 milliliters of 0.50 molar sodium hydroxide to 50 milliliters of 1.00 molar ammonium chloride. What's the pH of the resulting solution? And it gives you a Kb 1.8 times 10 to the minus 5. Okay, so like before, what I would do, this is some random base and acid being thrown together. Figure out what kind of quote-unquote titration it is, even though it's not a titration. And from there, you can figure out the region, find the corresponding equation, etc., etc. So see if you can do this problem on your own. I recommend pausing the video. When you want to talk about the answer, unpause it. We'll talk about it. Pause the video now. Okay, at this point, I'm assuming you've tried the problem. You want to talk about the answer, so let's get into it. So again, like before, figure out what kind of chemical species you have. Sodium hydroxide, strong base. Ammonium chloride, the chloride is pH boring, i.e. it doesn't affect it, but ammonium is a weak acid. So this is going to be like a weak acid plus strong base titration. And again, it's not a titration, but if we find the moles, we can use the corresponding equation to figure out what's going on. So weak acid plus strong base. Moles will come from molarity times volume. But before you do that, notice how the sodium hydroxide concentration is smaller than the concentration of ammonium chloride. And the volume of the sodium hydroxide is smaller than the volume of the ammonium chloride. So because the concentration and the volume are both greater for the weak acid than the strong base, that tells you that the moles of weak acid will certainly be larger than the moles of strong base. So this is the pre-equivalence region for a weak acid plus strong base titration. And there's different ways to do the pH at this point, but what I would do is I would use Henderson-Hasselbalch again. pH equals pKa plus log, and then it's base over acid. Now, we don't have any weak base initially in problems like this. We just have weak acid. However, if you looked at the alternative version of the HH equation when a strong base was added, in the numerator, the top part, it said NWB plus NSB. Well, moles of weak base are 0, but we do have some non-zero moles of strong base. So in the top part, you'll have moles of strong base. Now in the bottom, which is the acid part, you'll have moles of weak acid, and you'll subtract moles of strong base from that. So again, that's very sloppy. I'm sorry, it's hard to write on this thing, but it should say something like pH equals pKa plus log NSB over NWA minus NSB. So that's the equation you want. Now, notice that this is a Kb, all right? And we have a weak acid, A, all right, ammonium. So before you do pKa, you have to convert Kb to Ka, and then minus log of Ka will give you pKa. Or you could find pKb from Kb, and then 14 minus pKa would give you, pKb would give you pKa. Either way is fine, but make sure you do that conversion. NSB, NWA, those come from liters times moles per liter, so that's not too bad. And all of that should give you the pH. So let's look at the math. First thing I did was I solved for weak acid plus strong base. I made sure that was the kind. I'm thinking of it as a titration, even though it's not literally a titration. And next thing is to find out the region you're in. That's when you take the molarity times the times the volume, moles per liter times the concentration. So you get 0.05004 for weak acid, and you get 0.020 for the strong base. And again, moles of weak acid are greater than moles of strong base, so it's definitely pre-equivalence. And then here's the equation that I wrote out very sloppily earlier. pH equals pKa plus log moles of strong base on top divided by moles of weak acid minus moles of strong base. You have to convert pKa from Kb, so what I did is I went minus log of Kb to get pKb, and then 14 minus pKb gave me pKa. So you should use 9.26 here. But anyway, pH equals pKa plus log. There's all the mole values. When all is said and done, pH 9.08, good to go. That's the end of this chapter review for Exam 1. Thank you for spending your time with me. I know sometimes it's maybe not the most exciting thing to do, but you are awesome for being here. If you need more assistance getting ready for the midterm, there's lots of ways to get more help. There are practice problem sets online and in the companion that you can absolutely look at. The answers are given in the back of the problem sets, the practice problem sets, so try them out, see what you get. Concept guides and chapter guides will absolutely help as well. They're They're all online. Concept guides are in the companion as well. There's also end of the chapter problems in the textbook itself. Usually every other problem, the answer is given in the back, so you can try the problems, make sure you're getting the right answers. If you don't get the right answers, let me know. You can also reach out to me if you'd like and ask questions, all right? I can't help you on the midterm itself, but I can absolutely help you study for the midterm. So contact me. Also, you can contact the Learning Success Center /Avid Center if you need assistance studying for anything. That's not a problem at all. I know you can do this. You have all the skills to pay the bills. We just got to show you that you take care of business, all right? Okay, good luck with your studying. Thanks again for spending your time with me, and have a wonderful day.